In this lesson, we're going to be looking at rational functions, so functions that have x in the denominator. We're going to be looking at properties of those functions, how to find their asymptotes, and then using information we know about the first and second derivative of functions to help us sketch the graph of some rational functions. Before we jump into properties of rational functions, let's just do a quick warm-up question which reviews what we did in the last lesson, where it says find the intervals of concavity and the coordinates of any points of inflection for this polynomial function here. So remember, the second derivative tells us the concavity of a function. If the second derivative is positive, it tells us a function is concave up, and if the second derivative is negative, it tells us a function is concave down. And a point of inflection is a point where the function on either side of it is changing from concave up to concave down, or vice versa. A possible point of inflection would be at an x value where the second derivative is 0 or undefined. So let's start by finding the second derivative. So y prime, 3 times a third is 1, so I'd have x squared minus 24x plus 0. So there's the first derivative. The second derivative would be, if I differentiate this, I would get 2x minus 24. So a possible point of inflection will occur at an x value that would make this 0 or undefined. Well, that's just a linear function, it can't be undefined, but it could be 0. Let me set it to 0 and solve. If I did this, 24 equals 2x, x equals 12. And keep in mind, it says we want a point of inflection. Every point has an x and a y coordinate. So there's the x coordinate. How about the y coordinate? So where is the function when x is 12? So I'd plug 12 into this original function, and I'll evaluate what is the y value when x is 12. And I actually have this in Desmos for me. Let me set x to 12. And it says the y value is negative 1,147. Negative 1,147. So the point 12, negative 1147, is what we call a possible point of inflection. I know at that point the second derivative is 0. Now I have to check on either side of that x value of 12, what is the concavity of the original function? And if the function changes concavity on either side of an x value of 12, then we could then classify this as a point of inflection. So let's do that. Let's make ourselves a little table. In this table, let's put negative infinity on the far left, positive infinity on the far right, and that x value of 12 in between. This is going to divide our function into two intervals. One interval is between negative infinity and 12, so I need to pick an x value in that interval. I will pick 0. And then another one between 12 and infinity. I'll pick 20. So I need to test each of these x values in the second derivative of the function, so in y double prime, and then comment on what does that tell me about the original function. So when I plug 0 into the second derivative, I get negative 24, which is negative. That tells me the original function in this interval from negative infinity to 12 must be concave down. It must look like this. If I plug 20 into the second derivative, I would get positive 16, so positive, which means in that interval the function is concave up, which means it looks like this. So notice the function changes from concave down before an x value of 12 to concave up after an x value of 12, so that means at 12 there must be a point of inflection. So point of inflection at the point 12, negative 1147. And let me just show you this in Desmos. Pay attention to the value of the second derivative in the interval before an x value of 12. Notice how it's always negative in that interval. And then after an x value of 12, notice how the second derivative is always positive in that interval. And at the x value of 12, notice the second derivative was 0. So we just did all of that algebraically, and that made us conclude that there's a point of inflection at that point 12, negative 1147. The question also says to state the intervals of concavity. I mean, we kind of already have that here, but let's just state it formally. The function's concave down for all x values less than 12, and concave up for all x values greater than 12. All right, let's move on to part 2, where I give you a little bit of a reminder about stuff you would have learned in previous courses. So how do we find the asymptotes of rational functions? So notice I'm showing you a bunch of rational functions now. In all of them, we have a variable x in the denominator of the function. Let's look at these first 3 and see what's in common with the first 3 functions. Notice all 3 of them have horizontal asymptotes at y equals 0. And that's always going to be the case if in your rational function, the degree of the denominator is higher than the degree of the numerator. And let's look at all three of these functions. The first one, the degree of the denominator is 1. I can tell that because the highest degree term is 1. And the degree of the numerator, it's a constant, and constant terms are degree 0. So degree of denominator is 1, degree of numerator is 0. Denominator is higher degree than numerator, therefore horizontal asymptote at y equals 0. Second function, denominator is degree 2, numerator is degree 0. And third function, denominator is degree 2 again, numerator is degree 0. So in all three scenarios, the denominator is higher degree than numerator, so horizontal asymptote at y equals 0. They also all have vertical asymptotes. How do we know where the vertical asymptotes are? Well, the vertical asymptotes, no matter what type of rational function we have, are always at the x value that makes the denominator be 0. If we look at the first function, 2 would make the denominator be 0. That's why there's a vertical asymptote at x equals 2. The second function, we have x squared minus 4 in the denominator. How could that be 0? Well, if x was 2 or negative 2. That's why we see vertical asymptotes at those two spots. And the third function, 1 would make the denominator be 0. That's why there's a vertical asymptote at x equals 1. Okay, what if the degree of the numerator and denominator are the same? Where's the horizontal asymptote now? And in fact, the horizontal asymptote is going to be at the quotient of the leading coefficients in this scenario. The leading coefficient of the numerator is 3, of the denominator is 1. If we do 3 divided by 1, we get 3. Notice that's exactly where the horizontal asymptote is at, y equals 3. And we'll talk about why that is when we do asymptotes based on limits in a bit. But note, if the numerator and denominator are equal degree, you can find the horizontal asymptote by dividing their leading coefficients. And vertical asymptote, always same rule for that. What value of x makes the denominator 0? It would be 1. Therefore, vertical asymptote at 1. Last scenario, well, what if the degree of the denominator is less than the degree of the numerator? There's actually no horizontal asymptote. There's actually something called a slant asymptote, or sometimes called an oblique asymptote. How do we find this diagonal, this slant asymptote here? We can find the equation of that asymptote by actually finding the quotient of the numerator and denominator. So actually do x squared minus 1 divided by x plus 3 and get the quotient. If I were to divide those two functions, and maybe we would want to do this either long or synthetic division, doesn't matter. I'll set up a synthetic division table. X plus 3 is the divisor, so I put the 0 of that divisor here. X squared minus 1, the coefficients of that are 1, 0, and negative 1. Remember, we need a placeholder 0 because there's no degree 1 term in that dividend. It would be x squared plus 0x minus 1. If I do the synthetic division, I get this. I don't care about the remainder. That's not going to be of any use when talking about the slant asymptote. I just care about the quotient part of this. The quotient is x minus 3. And that's actually the equation of this slant asymptote. Let me just prove that to you quickly. Okay, here's this function. Oh, and we haven't talked about vertical asymptote yet. Vertical asymptote, always the same rule, right? What x value would make the denominator be 0 would be negative 3. That's why if I were to draw a vertical asymptote here, x equals negative 3, notice the function never touches that vertical asymptote. But because the numerator is higher degree than denominator, there's no horizontal asymptote, there's a slant asymptote. And the quotient, 1x minus 3, should tell us where that is. Let me graph the function y equals x minus 3. Notice, the function never touches that line either. No matter how far I go, the function will just keep getting closer and closer and closer to that dotted line and will never touch it. So to find a slant asymptote, you actually have to do the division and find the quotient, and the quotient tells you the equation of the slant asymptote. Slant asymptote at y equals x minus 3. Now I've said up until now any x value that makes the denominator 0 is a vertical asymptote, and that's actually not the whole truth. An x value that makes the denominator be 0 could be a vertical asymptote or a hole in the graph. If we look at this graph right here, notice there's a hole in the graph right there at an x value of 2. And if we look at the equation, let's look as to why that is. Why on this graph is there a vertical asymptote at x equals 1, but a hole in the graph at x equals 2? Because both of those numbers make the denominator be 0. If I were to plug 1 into the f at x function, I would get negative 1 over 0. I would get a number over 0. When that occurs, you get a vertical asymptote at that x value. But if I were to plug 2 into this function, I would get 0 over 0. If you get 0 over 0, that means there is a hole in the graph of that x value, not a vertical asymptote. In order to figure out where the hole is, well, if we simplified this function would be equal to, well, those would cancel as long as x isn't 2. So this is equal to 1 over x minus 1, as long as x is not 2. So it's equal to this as long as x isn't 2. Because if x is 2, well, the function, this version of the function actually exists when x is 2, but this one clearly does not. But if I were to simplify it and take out those factors of x minus 2 and plug 2 into this version of the equation where I say x isn't supposed to be, well, where would the function be if we took that hole out? We'll just plug 2 into the simplified version. I'd get 1 over 2 minus 1. That's 1 over 1, which is 1. So that's why I know the hole is at the point 2, 1. Because if we remove the discontinuity, which means do this simplification where I cancel the factors that cause the hole, and then plug the x value in, it'll tell me where the function would be if the hole wasn't there. So general conclusion, if you get a number over 0 for a given x value, that means there's a vertical asymptote there. If you get 0 over 0 for a given x value, that means there's a hole in the graph at that x value. Okay, let's talk about this next section. This may be a little bit of a new way of thinking about asymptotes for you. We've talked about limits earlier in this course, and in your previous course as well. But let's talk about how limits can tell us where asymptotes are. So for a rational function where we have f at x over g at x, there's a vertical asymptote at an x value of a if the denominator is 0 at that value of a, so if g at a is 0, and if the limit as x approaches a, so as I plug in x values that approach a into this whole function, I get plus or minus infinity. That means the function is getting infinitely close to that vertical asymptote but never touching it. It's going infinitely high and low. And if we look here, notice to the right of the vertical asymptote, as I approach that vertical asymptote, the function's going infinitely high. It's going to infinity. And to the left, as I approach the vertical asymptote, it's going infinitely low. It's approaching negative infinity. And let me just show you on here. Pay attention to the value of the function. I'm going to approach an x value of 1 from the left. So pay attention to that point. Look at the y values as I approach an x value of 1 from the left. The y values are going down, 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 down. They're going to go infinitely low. They're going to go all the way down to, we say, negative infinity. How do we find horizontal asymptotes? We say there's a horizontal asymptote at y equals L when the limit as x goes to infinity or negative infinity, what is the quotient going towards? So basically, as I plug in infinitely small or large values of x, what's happening to the y value? Pay attention to the blue point and also to the y values I have here. You could look at the y value of the labeled point. What's happening to that y value as x gets infinitely big? As x goes to infinity, right now x is at 4, as I make that infinitely big, what's happening to the y value? The y value is getting closer and closer and closer and closer to 0. And no matter how far I go, I keep getting closer and closer and closer to 0. Like right now it's at 0.014, but I never actually get to 0. But it's approaching 0. And the same thing would be happening if I move to the left. As x goes to negative infinity, the y value is going to 0 in that direction as well. It just keeps getting closer and closer to that horizontal asymptote. But remember, a horizontal asymptote only exists if the degree of the numerator is equal to or less than the degree of the denominator. If the numerator is a higher degree than the denominator, then there's a slant asymptote. Okay, let's move on to part 3 where we actually start doing some examples with this new information. So example 1 says, state the horizontal asymptotes of the following functions. So I have two functions here. Let's find the horizontal asymptotes of each of them. Part A, notice the numerator is degree 2, and the denominator is also degree 2. So when the numerator and the denominator are the same degree, you can find the equation of the horizontal asymptote by finding the quotient of the leading coefficients. So we will do 3 divided by 6, which is a half, which means our horizontal asymptote is at y equals a half. Part B, the numerator is degree 2, but the denominator is degree 3. When the denominator is higher degree than the numerator, there's no calculation necessary for the horizontal asymptote. We know it's just at y equals 0. Let's move on to example 2, where we're actually going to start graphing some rational functions. Here's our rational function. Notice the numerator is just a constant term, which is degree 0, and the denominator is a quadratic in factored form, so it's degree 2. Part A says find the asymptotes. Well, since the denominator is higher degree than the numerator, I know there is a horizontal asymptote at y equals 0. Vertical asymptotes are at places that make the denominator be 0. So what x value would make the denominator be 0? Well, since it's in factored form, I can see that an x value of -2 would make that factor be 0, which means the whole denominator would become 0. And I know an x value of 3 would make this factor be 0, which would then make the whole denominator be 0. So there are vertical asymptotes at x equals -2 and at x equals 3. Part B, this is new. It says find the one-sided limits as the x values approach the vertical asymptotes. And it tells you how to do that because this is the first time we're doing this. It says sub values very close to the limit for x and find what the value of the function is approaching. And when I say the value of the function, remember I'm talking about the y values of the function. Since this is our first time evaluating one-sided limits, let me show you the graph to hopefully try and explain to you what that means, and then we'll evaluate from there. So here's the graph of the function, and notice there are vertical asymptotes at x equals -2 and x equals 3. We want to evaluate the one-sided limits as we approach those vertical asymptotes. So let's look at the x value of -2 first. As I approach an x value of -2 from the left, notice this point is on the function to the left of that vertical asymptote. As I approach that vertical asymptote, we want to pay attention to what's happening to the y values. So you can either look at the y values on the point here, or I have Desmos showing us the calculated y value here. We want to know what are those y values approaching as the x value approaches -2 from the left of -2, which is where this point is. So as I approach that vertical asymptote, what's happening to the y values? They start going higher and higher and higher and higher. Oh, they start going very high. This function is going to get infinitely close to that vertical asymptote, but it's never actually going to touch. And if I zoom in, you can see that it's never actually touching that vertical asymptote. It'll just get infinitely close. So that means as we get closer to -2 from the left of -2, the y values are going infinitely high. They're going up to, we'd say, positive infinity. Now at -2, the function is undefined. You can see that calculation there. But as we get infinitely close, the y values are going infinitely high. And let me make it go even closer to -2. So right now it's calculating when x is -2.01. What if I had a few more zeros in there before the 1? So -2.00001. Notice what's the y value? It's almost 20,000. It's very high. So the y values are clearly going off to infinity. Let's write that down. So we want to write what we just did. We'd say the limit as x is approaching -2 from the left of -2, and we communicated it's from the left with that little minus sign in superscript above the -2. So the limit as x approaches -2 from the left, and we're doing the limit of the y values of the function. So I can say the limit of f at x, because that's what our function is named here. I could have also written the whole equation, but I think it was more efficient just to write the name f at x. That means the y values of the function. So the limit of the y values of the function as x is approaching -2 from the left is equal to infinity. And how did we get that? Well, we did a little test. We did a test point. We evaluated f at a point really close to -2 from the left of -2. We did -2.00001. And we got, it was like 19,999.96. That told us that the y values were going infinitely high. That's how we figured out that it was going towards infinity. We also need to figure out what is the limit as x approaches -2 from the right of -2. So let's do that now as well. Let's find the limit of the y values of the function as x approaches -2, but this time from the right of -2. That's what that little plus sign means. It means from the right. So let's go back to our graph, and now let's move to the right of -2. So I now put a point on the function to the right of the vertical asymptote at x equals -2. And as I approach that x value of -2 from the right of it, so as I move this point closer to that vertical asymptote, let's pay attention to the y values. They start going infinitely low. Notice when x is -1.99, the y value is -20. How about if I make it go even closer? So like negative 1.9999. The y value into negative 2,000. So the y values, as I get infinitely close, notice, are going to be going to negative infinity. So we know the limit of f at x, as x goes to negative 2 from the right of negative 2, the y values are going to negative infinity. They're going infinitely low. And we figured that out by doing a test point to the right of negative 2 that's very close to negative 2. And our test point, we used negative 1.9999. And we got a calculated y value of negative 2,000.04, which is what shows us that the function is going towards negative infinity. Let's do the same thing, but around the other vertical asymptote. So the other vertical asymptote was at x equals 3. So we need the limit as x approaches 3 from the left, and it's the limit of the y values of the function. So we would need to pick a test point that's very close to 3, but to the left of 3. So we could do like 2.9999. Throw in more 9s if you want to make it even closer, but this should be good enough for us to see whether it's going to positive or negative infinity. Okay, so I have a point to the left of the vertical asymptote at x equals 3, and let's move the point closer. The y values start going infinitely low. And if I set it equal to 2.9999, the calculated y value is negative 2,000.04. So the calculated value is negative 2,000.04, which tells us the limit of f at x as x approaches 3 from the left is negative infinity. The function is going towards negative infinity as we approach 3 from the left. How about if we approach 3 from the right? Where's the function going? The limit of f at x as we approach an x value of 3 from the right side of 3 would be equal to, and we'll have to pick a test value to calculate this. Because remember, we don't actually have the graph, I'm just showing that to you. So our test value, we could do a number really close to 3, but to the right of 3, so like 3.00001, and throw in more zeros before the 1 if you want to get even closer, but this should be fine. Let's calculate that. So let's move to the right of the vertical asymptote at x equals 3. Okay, notice my point is to the right of the vertical asymptote of x equals 3, and let's move the point infinitely close to it. What's happening to the y values? The y values start going infinitely high. If I evaluate at 3.00001, I get a y value of almost 20,000. That 19,999.96. which tells us that the limit is going towards infinity. And now I know you don't have Desmos calculating these y values for you, but we would just be plugging these x values into this f at x function and calculating. So using all of those one-sided limits, we should be able to sketch a pretty accurate graph. So let's start by graphing our vertical and horizontal asymptotes. So the vertical asymptotes were at x equals negative 2 and x equals 3. And the horizontal asymptote was at y equals 0. And now we should be able to do a rough sketch of this function based on its one-sided limits. We'll get the right shape of the function. It won't go through all the perfect points that it's supposed to, but that's okay. We're just worried about getting the right shape here. So where's the function before an x value of negative 2? Well, let's look at the one-sided limit as x approaches negative 2 from the left of it. As x approaches negative 2 from the left, the y values are going to infinity, which means the function must look like this. It must be going up to infinity as we get closer to negative 2 from the left of it. And we know that as x goes to negative infinity, the function is going to be approaching that horizontal asymptote, which is why I have it getting closer and closer and closer to that horizontal asymptote there. Now, what's happening to the right side of negative 2 as I approach negative 2 from the right? As I approach negative 2 from the right, the function's going down to negative infinity. So as I approach an x value of negative 2 from the right of negative 2, the function has to be going down to negative infinity. What happens as I approach an x value of 3 from the left of 3? Approach an x value of 3 from the left of 3, the function's also going down to negative infinity. So it needs to look like this. Now once again, in here, it's not going through all the proper points that it should, but it's got the proper shape. And now what happens to the right of an x value of 3 as I approach 3? The limit tells me that the y values are going towards infinity. So from the right of 3, as I approach 3, I need to be going towards infinity. So that's a general shape of what this function would look like. And there's the Desmos graph of the function. Notice our shape, really close to that one. Okay, our last example for this lesson. Consider this function, which has degree 0 in the numerator, degree 2 in the denominator again. It says where are the vertical and horizontal asymptotes? Well, since the denominator is higher degree than the numerator, I know there's a horizontal asymptote at y equals 0. And vertical asymptotes are at the x values that make the denominator be 0. But look, can x squared plus 1 be 0? If we tried to solve this, we'd have x equals plus or minus the square root of negative 1, which means there's no real solutions to that equation I made. Therefore, which means there's no way x squared plus 1 can be 0, which means there are no vertical asymptotes. Okay, so we're not going to be able to graph this with one-sided limits because we have no vertical asymptotes to approach. What we're going to do instead is find local max and min points and the intervals of increase and decrease, and then we're going to find points of inflection, and then we're going to sketch a graph of the function. So find any local max min points in the intervals of increase and decrease. Well, I can find local max min points by testing critical numbers using the first or second derivative test. So I'm going to have to start by finding critical numbers. Critical numbers are numbers that make the derivative be either 0 or undefined. So let's start by finding the derivative. So f prime of x equals, now this is a quotient, so I'll use quotient rule. Derivative of the numerator is 0 times the denominator minus derivative of the denominator times the numerator all over the denominator squared. And then we'll simplify this. This would simplify to negative 2x over x squared plus 1 squared. Now, a critical number is a number that would make this be either 0 or undefined. It would be undefined if there was an x value that would make the denominator be 0, but we've already established x plus 1 can't be 0, so we don't have a way that this could be undefined. But could this fraction be 0? Yeah, a fraction is 0 if the numerator is 0. So just set the numerator to 0 and solve that, and we would get x equals 0. That is our critical number. So let's find our critical point by plugging 0 into the original equation and evaluating. So our critical point would be the point 0, f at 0. But let's evaluate f at 0. If I evaluated f at 0, I'd get 1 over 0 squared plus 1. That's just 1 over 1, which is 1. So f at 0 is 1. So my critical point is the point 0, 1. This might be a local max or a local min point. Let me actually test to see if it's a local max or min point, either using the first or second derivative test. Since finding the second derivative may be a little complicated, since I'd have to use quotient rule and chain rule, let me instead do the first derivative test. So I need to make a table where I test on either side of that critical number to see if the function is increasing or decreasing. So I'm going to set up my intervals. My critical number was at 0, and I want to test a number in each of those intervals I created in the first derivative, and then state what that tells me about the original function, and then I should be able to conclude whether there are local max or min points. So between negative infinity and 0, I'll choose negative 1, and between 0 and infinity, I'll choose 1. Plug each of those numbers into my first derivative. If I plug negative 1 in, I'll just do that over here. F prime at negative 1 would equal 2 over 4, which is a half, which is positive, which means the original function is increasing in the interval before that critical point. If I evaluated f prime at 1, I would have negative 2 over 4, so negative a half, which is negative, which tells me the function is decreasing in the interval following the critical number of 0. So it was increasing before the critical number of 0, decreasing after the critical number, which means at that critical number, there must be a local max. So there's a local max at the critical point 0, 1. It also says state the intervals of increase and decrease. So let's state that as well. When is this function decreasing? And when is this function increasing? And we have that in our table. Let's just write it down here. The function is decreasing when x is greater than 0 and increasing when x is less than 0. If Part C says find the points of inflection. Okay, I am going to need the second derivative. So I suppose I could have found that back here and then used the second derivative test. But we'll find the second derivative now. So let me just rewrite the first derivative, f prime of x. Okay, we're going to have to do quotient rule. So f double prime of x, derivative of numerator times the denominator, minus the derivative of the denominator, which I'll have to do chain rule, bring the exponent down, keep the base, reduce the exponent by 1, and then multiply by the derivative of the inside function, which is the base of the power. So the derivative of x squared plus 1 is 2x. And then that needs to be multiplied by the function in the numerator, so negative 2x. And this is all over the denominator squared. So x squared plus 1 squared squared. Let's do some simplifying. F double prime of x equals negative 2x squared plus 1 squared. I'll leave that for now. Notice I have a 2 times a 2x times a negative 2x. That product would be negative 8x squared. So I'll be subtracting a negative 8x squared, which I'll just write as plus 8x squared. And then don't forget I have this factor of x squared plus 1. Oh, and then I need to rewrite the denominator. So I have an x squared plus 1 squared squared, which I could just write as to the power of 4. Now let me common factor the numerator. I'm going to take out a negative 2 and an x squared plus 1 from both terms. So from the first term, this, when I take out a negative 2 and an x squared plus 1 from that term, I'm left with x squared plus 1. And when I divide this by negative 2 and x squared plus 1, I get minus 4x squared. And this is all over x squared plus 1 to the 4. We can do some more simplifying here. That factor cancels with one of those. So I have f double prime of x equals negative 2. In the square brackets, I have x squared minus 4x squared. That's negative 3x squared plus 1 over x squared plus 1 cubed. So this is my fully simplified version of the second derivative. And I forgot to explain why I'm even finding this, right? Why am I bother finding the second derivative? Well, if I want points of inflection, I know at a point of inflection, the second derivative is either 0 or undefined. So I need to find the second derivative, now figure out how can this be 0 or undefined, and those are my possible points of inflection. I can verify if they are or not by testing concavity on either side of those possible points of inflection. So how can this be undefined? Well, how can the denominator be 0? We've already established that denominator cannot be 0 because x squared plus 1 can't be 0, so this can't be undefined. But could it be 0? A fraction is 0 if the numerator is 0. Can negative 2 times negative 3x squared plus 1, can that be 0? Yeah, I'm pretty sure it can. This product would be 0 if the negative 3x squared plus 1 was 0. Right? Let's just divide the negative 2 to the other side. It's gone. Now solve this. I'd have 3x squared equals 1. X squared equals a third. X equals plus or minus the square root of 1 over 3. And we could get approximate values for this. Approximately plus or minus. It's about plus or minus 0.58. So the possible points of inflection are going to occur at those x values. Let's find the 2 points. So our possible points of inflection are, so possible points of inflection, they're going to occur at an x value of negative 0.58 and some y value. We'll have to plug it in to figure it out. And positive 0.58 and some y value. Okay, now I need to get the y values that go with each of those x values by plugging those x values into the equation of the original function, which is right here. I'll just get Desmos to do the calculation for me so that I can get an exact value. So when I plug in negative 1 over root 3, notice the calculated y value of the original function is 0.75. When I plug in positive 1 over root 3, hey, the calculated y value is still positive 0.75. So these 2 points here are my possible points of inflection. I just have to check on either side of these points, does the function change concavity? Does it change from concave up to concave down or vice versa? If it does, then we have points of inflection. And I can test the concavity by plugging in test values into the second derivative, seeing if the second derivative is positive or negative. So my calculated y values for both of these were 0.75. And now I have to check if these are in fact points of inflection. So like I said, we need to test x values in the second derivative around those possible points. So I'll set up a table that looks similar to the first derivative test. I'm going to have negative infinity, positive infinity, and the x values of the possible points of inflection in between, putting them in ascending order. So my negative 0.58 and my positive 0.58, right? Those are my plus or minus 1 over root 3 values. And then I'm going to choose an x value within each of those intervals I've created, test those x values in the second derivative, see if I get a positive or negative answer, and then that tells me if the original function is concave up or concave down. So I'm going to choose the x values negative 1, 0, 1, plug each of them into the second derivative. So into the second derivative, I will plug negative 1, right? Look at the second derivative. It's positive there. So at this point, the function is concave up. So second derivative is positive, which means concave up. Looks something like that. In the next interval, I chose a test value of 0. So that means at that point, the second derivative is negative, which means at that point, the function is concave down. Negative, so concave down. And in my third interval, I chose a test value of 1. If we look at the second derivative, it's positive there. So at that point, the function is concave up. So in my last interval, the second derivative is positive, which means the function is concave up in that interval. Since there's a change of concavity around each of the x values of the critical points, right, it switches from concave up before negative 0.58 to concave down after. Since there's a change in concavity, we know that at negative 0.58, it's a point of inflection. So there are points of inflection at negative 0.58, 0.75, and at 0.58, 0.75. Using all the information we have from part A, B, and C, we should be able to graph a pretty accurate sketch of this function. So this function has a horizontal asymptote, so let me draw that in. And it was at y equals 0. It had no vertical asymptotes. But we know a couple points of inflection, and we know a local max point. There was a local max at the point 0, 1. So let me plot that. Right here, there's a local maximum point. And there were 2 points of inflection. So that's like here. And also at positive 0.58, 0.75. That's about here. And I also know the intervals of increasing and decreasing. The function had to be increasing before an x value of 0 and decreasing after. So I need, before an x value of 0, I have to be increasing in concave up at that part, then increasing in concave down in this part, decreasing in concave down in this part, but then decreasing in concave up in this part. So there's a rough sketch of what the function looks like. And if we look at the Desmos graph of the function, it looks pretty good. Okay, that's it for our lesson on rational functions. In our next lesson, we're going to do lots more curve sketching examples.